Hi guys. Today I would like to let you know that we're starting a project on YouTube that you can follow along with, and periodically, as I would like to do this every day almost, where we will be posting new developments on the project. It's pretty much something for you to go along with, and we will be developing an orchestrator. I will show you some more about this Borg architecture we will be lending ideas from, as well as Kubernetes. And by the end of it, you'll probably know how to code in Go. You'll know a little bit about a orchestrator pattern more, and also you'll be able to learn some TLA plus and how to think about concurrent code and systems. Um, Myself and I have a couple other guys who want to join in as well and work on the code. And yeah, it's pretty much to have some fun. Um, and I hope you join us for the ride. So at the bottom, you'll find the GitHub repo. And yeah, let's just get going. Today, I'm going to introduce a project that we will be building. It's going to be an orchestrator pattern that we're going to do in Go. And we will initially design this thing in TLA plus PlusCal. And so the question is, what is an orchestrator? Right? An orchestrator essentially is a design pattern for cloud computing that allows you to manage containerized applications at scale. And this can be quite tough without an orchestrator, hence its use. So what an orchestrator is a tool to automate the deployment, scaling, and managing of containerized applications. You can think of it as a conductor of an orchestra. Keep all of these containers working in harmony. One well-known orchestrator that we will be discussing is Borg from Google, which has been used for a long time and was praised for its scalability and fault tolerance. A short introduction of Borg. Its use case is to manage containerized applications across massive server clusters. It automatically schedules containers on available machines and notes failures by restarting containers on healthy machines and ensures efficient resource utilization. However, in recent times, Kubernetes has become more popular for its orchestration capabilities. So Kubernetes is different to Borg in that it is open source. Anyone can contribute to it. It offers a more declarative approach to managing applications where you define the desired state and Kubernetes takes care of achieving it. So if we compare the two of them, both of them are powerful orchestrators, but they offer different requirements. So Borg is excellent for large-scale deployments within a single organization, while Kubernetes is more flexible and portable, making it suitable for various environments, for on-premises, cloud, and hybrid app deployments. So that's an introduction. And now we will go into looking at the architecture of them in diagram form, as well as the TLA plus specification. We can start with Kubernetes. And when we look at this, we see that Kubernetes has a master node and a worker node in its cluster, right? And inside this worker node, we look and we see that it has a container. Inside the pod, it has a runtime, and our master node has references to a scheduler and a controller manager. What this allows us to see is that we have all these components that we need to think about in our design. So one is a worker, one is the master. There'll be more than one worker, but also we can think of it as a client as well that's going to access the system via the master node, which will again send the work on and request work to be done by the workers. This allows us now to realize, okay, we need these four entities. I'm going to show you in the TLA spec how I'm going to omit the scheduler just for now, and we will go further. Now let us take a look at Borg. So this is Borg, and now you can see it's somewhat similar. Okay, they call it a Borg master, but we just call it the manager. They have Borglets, but we just call them workers. And there's a scheduler. And what happens again is that a client will have to access the system via the master, which will designate the work to be done on the workers. And now we know, okay, these four entities we must think about in our application. And now let us go over to TLA plus or PlusCal, where we can actually start to design our system. And this is our TLA specification, at least a start to the orchestrator that we have done. Please note that you will need to have 4 dashed lines at least before the name module. Then whichever you choose, orchestrator should be the same as the file name, and then 4 dashes afterward at least. Then at the bottom of your file, you will need also these double dash over here and 4 of those at least. And what we are going to do is not to write directly TLA plus, but rather PlusCal in the P style. Let us first look at the extended packages or modules that we will be using and the functions or the operators that we have. In the naturals, we will define a set of natural numbers. In TLC, we're going to be using the assert value over here. We will be asserting whether value is true or false. In the sequences package, we will be using the append to append a value to a sequence S. We will be using the head to get the first value in a sequence, and a tail to get the rest of the values, excluding the head of that sequence. And then we will also be using the length of S, where the way one would read this is that we choose or we have an arbitrary in the natural numbers, or all the natural numbers, the set of them, such that the domain of S is equal to 1 to n. That's what that means over there. So we can get the length. This is the orchestrator that we have now built. I've only built a very small version of it, but I will now go through what you're looking at. We have constants, which are workers, a set of them, a set of managers or clients. I intend to use one manager, and I intend to use, at the beginning at least, one client. I have messages. These will be these are a description of all the messages that can be sent within the system. The first message is a task, which will be from a manager, as in S, being sent to a worker or one of the workers, the receiver. We union that value, and what we're saying is that this is being unioned to the next record of messages, is being unioned to the next. That's what cup means. It can easily be replaced by simply saying union. That's equivalent. We say that we have a type of message that could be in the set of working, completed, or waiting, sent from the workers to the manager. Then we say also that the manager can send a message of in progress or finished to the client. And then the do work is what the clients send to the managers. This is how they will be communicating. These three entities will be able to tell each other what work they need to do and what state they are in, so that they can complete the running of the containers and doing useful work within the system. Here I say that I want my actors to be the workers, union again. If this is easier for you, just use union, to the managers, to the clients. So we create a set of them. And then what we say is, this is a syntax to start an algorithm or an orchestrator. This can be any name you want. But if you start this algorithm over here, that clause, you must also end it like this. This will be translated into TLA plus, because this is PlusCal that you're looking at right now. Effectively, the P-style algorithm to describe PlusCal. Then we have variables. The messages are empty in the beginning, which makes sense. That's the initial state. And because we are initiating, we put equals there. If we were assigning, we would put dash equals. For W state, which is the worker state, we say that for all the workers, they must all be waiting, because they obviously didn't get any work in the beginning. Manager state will be all the managers, which consist of one manager, is ready to receive its work. The client state for all the clients will be idle in the beginning, right? And the queues, what we're saying here is that for every actor in the system, it will have an empty queue at the beginning. And this queue will be, we could pass messages or text or whatever for work to be done. So we could pass even numbers 1, 2, 3, and it will have to process those. Because what we're doing is we're trying to model the system and try to make it as simple as possible. So that's why we might use numbers, but we can change it as we wish. And just to say also, one thing to add, TLA plus is not having type checking. So you should think about that. It's your job to write the spec so that you make sure that you're not sending strings when you should be sending numbers, etc. So it actually makes sense when you're model checking it. And then we have a macro for send. What we are saying is that when we send, there will be some sort of item that is sending it. Right? Let's say a client is sending a message, and we're going to take the queue, right, is equal to the append queues for that particular ID, and we append the message to that queue. What we also say is that when we receive a message, we await for the length of that message to be greater than 0. We say the message, we give a value to it. Now we're assigning the head is equal to the message, and the queues is going to be the tail of the queues for that particular process that is accessing it. These macros must always end with an end macro clause. So this is how we do it. Macro, begin, end macro. As you can see, I haven't implemented anything fully yet. I've just started to flesh out the ideas. That's why we have skip over there. But this is not a fair process of workers. And the worker queue, we might just leave that there for now, but take it away later. And always end your process and begin it. The process for the set of clients, I also put a variable there just in case I might need it. And then for one of the actions called send task to manager, what we are saying here is that if the message, this particular queue is empty, right? Then, well, that's actually not a queue, it's a sequence. Then I want you to, with the set of managers, right, with M in the set of managers, I want you to send a message where that self gets sent. So effectively the client, whichever client that is, if there's two clients, we know that one of them is going to be the self. The type of message sent is do work, and the sender is self, and the receiver is a manager, which makes sense because that's what we defined in messages above. When we receive a task that is finished, we are saying that in the set of managers, if the messages of the task is finished, meaning that the messages that we have has a message called finished on it, then the M state of that particular manager for the M must be done, right? And that's what we're saying. This is a and, yeah. So these two must be true. Then we are allowed to receive a message. So a client can receive a message under these conditions. Else we go to the send task manager, which will send a task to a manager for that particular client when it doesn't have when it is not receiving a message, and we end the process. And please remember to always end with and end if. It's a very common error. The process of managers, we're only going to have one manager in our set, and we're saying that we always begin right and always end process, but the notify client of completed job. So we're saying for that action, if the message type is completed, then for the set of clients, do send, right? So now we're going to send finished from this particular manager self to our receiver, which is a client in C, and the S, the sender, is self. I hope that makes sense. And end with and end if. Always, please remember. Now we have skip here and skip this because this is the work that we will do. If we run this particular, I'm going to first save it because it must be saved first, or there will be an asterisk over there. We will translate it with Command T. You can also do translate PlusCal algorithm, and you're going to get all of this here. By the way, I'm going to show you why this is failing. If we model check it, by the way, you can just make a model over here. You say new model, and when we run it, it should fail because of course we haven't implemented many parts. And if we go back, we can actually click in here, by the way. So click in there, and there's nothing, no messages, but it says that this thing isn't being called, right? Or it's never enabled. And that just means we have more work to do. We've got to write out this thing. So that's it for this part. And from here, I want to go now and just start to put a skeleton on Golang. This is our demo repo where we will be making our orchestrator. We are doing this in Go because it's a much easier language to do it in. But you could take the PlusCal translation and you could do any language you wanted. You could design your system in, because the PlusCal is simply an abstraction of your code where you can check it and model it and think through it. So I'm going to suggest that you try and get one of these images going, where I use actually the Dapper container image to do a dev container locally, so I have everything set up for Go. Right now, we're going to be looking at some of the code that we'll be writing and just playing around with what we're doing here. Let's start with the client. A client, we're just adding a bunch of UUIDs because we want to know that who the client is. And we're going to have a queue. So we're using Google's queue to allow us to send messages on the queue, which we defined for every single process in our system. I use that queue notation over there. It makes it easier, but you can use anywhere you want. And this is a channel, a send stream, which is allowed to send strings. We can change this to Int32s or whatever you want. We're just trying to mess around with it right now so we can send messages across and to communicate. The manager, we are saying that this manager must be a server, right? So it must therefore it must be able to handle requests at a particular endpoint. And what happens is I'm just beginning with writing it like now. This code I actually had generated by AI. So this, you can see, is very easy to simply, once you know what you want and you've designed it using PlusCal or TLA+, you can simply go to a code generator and make the code for you. It becomes a lot easier, and at least then you know that the code is correct if it passes model checking. A task, I actually saw a post about this, that we want to have our tasks inside of here. So we can simply say task, so that when an event gets sent, it contains a task. And the name, we could just make it like, it could be this time. For now, this must still be fleshed out further, but what we are saying is that our task might very well be a container and our worker must be able to take these. So I've been just messing around with this thing where our worker might do some search algorithms or whatever. And what happens is that this is a work in progress. And what we're doing at this moment is taking our TLA plus and going over into our Go periodically just to see what we can do and play and develop it as fast as possible, but also making sure it's correct. And of course, the main.go is simply a package where we're starting from. And this is where we can write our execution code. We can run our integration tests from here. We can write them. But I would suggest that for every single one of these folders that we have an additional one called manager. We So we can write some tests here, whatever, and that's really the point. So package manager, blah, blah, blah. And this way we can keep our tests and for each and every one of our components together. And that's it. We have so far built a small piece of our TLA plus spec. We've also built some parts of the Golang, and in the next episode, we're going to be building a lot more features in our Golang, as well as further iterating upon our TLA plus spec. Thanks for watching, and I hope to see you soon. The code is at the GitHub link below, and yeah, please contribute if you feel like it, or just watch the series. And if you like what we saw, please like and subscribe so that you don't miss any episodes that will be coming out. Thanks for watching.